At the risk of putting you all to sleep or not, maybe I should turn on a few more lights. What do you think?
Probably need that for sure, though.
That might be too many, but we'll see. Anyway, I'll let people in the background play with that. Yeah? Okay. Originally, I was supposed to give a keynote for session 4, so the focus of my talk is largely going to be on in situ permeability and hydraulically induced fractures in controlling fluid flow into wells and the insights from petroleum systems that bear on that. And in situ is in quotes to refer to pre-drill permeability of whatever origin, including but not limited to matrix, porosity, vugs, and fractures at all scales, as distinguished from drilling-induced or hydraulic fracturing that we do, things we do during the completion of the wells, okay? And I was going to talk about this, starting with what we think we know. And a lot of this is, I think, going to be actually quite repetitious with what you already heard Rick say. So if he was expecting some kind of big debate, maybe there won't be, but we are coming at it from a different perspective and with slightly different emphases. So perhaps there is value, and repetition is not necessarily a bad thing, because it's nice to know where there is consensus, and if you were asleep the first time, then you get to hear it again anyway. So there, yeah. Matrix porosity has to provide the storage. If there isn't any matrix porosity, then you're essentially in a hot, dry rock, EGS kind of regime, and there's no value to being in a sedimentary basin pursuing sedimentary heat. But also I say that because it's a very tall ask for natural fracture systems to have porosities that are even in the range of 1%. In karstic situations, you might get average porosities that are of the order of 0.5% that might be attributed to, quote, fracturing. But generally, fracture porosities are 1 or 2 orders of magnitude less than 1%. And something has to provide the storage for these geothermal fluids. If you're going to produce that fluid, it has to come from somewhere and it has to be equilibrated with the rock, the temperature. So we'll talk a little bit about the origin and preservation of matrix porosity, but you'll have a chance to look at that in more detail in sessions 3, 8, 11, and perhaps others later in the week. I'm going to assert that naturally producing fractured horizons or reservoirs can be divided into 3 types, but this is as arbitrary as any other division that one might make. Say a little bit about how you can tell that fractures are present. Then I want to say a few words about anisotropy. Non-uniformity is probably the norm in the subsurface, and as Rick's last slides or models might have indicated, anisotropy is probably not your friend, and I think you'll see that further in the session on modeling, session 6, if not before, when it comes to heat extraction. And hopefully we'll have time to enumerate some of the things we don't know. And the 2 most on my mind are shown here, but you may have other favorite unknowns, and it would certainly be good over the course of this week if we could have a discussion about this and agree what might be the critical ones. And I want to broaden the conversation by representing or reintroducing some discussion from the 2011 workshop that John mentioned. And so to do that, I'm actually going to begin with the end in mind to make sure that I get to that. And you can consider this to be my key slides, my key issue slides if you want to. In terms of insights from petroleum systems, porosity has to provide the massively connected storage. If you want to produce 50,000 barrels a day or 100,000 barrels a day at temperature, then that fluid has to be in the subsurface equilibrating with the host rock for some time. So you have to have not 50,000 or 100,000 barrels of storage down there, but you have to multiply that times however long you think you need to equilibrate with the rock. And that's the minimum volume you need down there. And that volume has to be connected to the wellbore through some permeability system. So it has to be massively connected in some way. As Rick indicated, 30 to 50,000 barrels a day over the life of a well is a big ask. It's not outside the bounds of the biggest wells at their peak production times, but it's perhaps above the P50, even for the top 100 wells in the most prolific plays, even correcting the oil production, which is what we like to talk about, of course, for water production and gas production. And Roberta will tell you we produce far more water in the oil and gas industry than we actually do oil, so clearly some kind of correction for that is needed, but exactly what that might be is maybe more difficult to say. And also then anisotropy is likely to be pervasive in the subsurface. It occurs on multiple scales and it's not your friend. But there's more that we can learn from oil and gas operations, and while not strictly geological in nature, I think I would be remiss if I didn't talk about some of these risks and stressors associated with Sedheat that we encounter in our oil and gas operations. And the first is water utilization, and water utilization competition can take many forms. It may be an intermittent stressor arising only in drought times, or it may be pervasive as in the American West. And what that means is that any additional petitioner who wants access to water is going to face serious obstacles in the public arena. Potable or agricultural use aquifer contamination is a big issue. It includes wastewater disposal as well as primary production system leaks and spills. The former, wastewater disposal, could be a big issue if you're not planning a closed-loop system, whether you're talking about water treatment costs, parasitic losses to run injection systems, or for induced seismicity risks associated with large volume injection into new horizons, or even the existing horizons. So for both injection and production wells, how does one monitor to assure or to prove to skeptics that you have well integrity during the life of the well at high temperature? I don't have the answer to that question, but it's clearly something that we might need to think about. Induced seismicity. Given the throughput that we want, not only is there likely to be a large pressure drop between injector and producer, creating seismicity concerns in the varying pore pressure regimes, but if injection and production get out of balance, then we could have either inflation or subsidence with the associated risks to damaging surface and subsurface infrastructure. If we're looking for natural fractures that are highly permeable and connected, we often look in regimes where there is a tectonic overprint, multiply intersecting domains, and those are likely to be the most seismically active areas that we could possibly want to inject into. So we're starting out trying to locate injection wells in areas where we would not locate fluid disposal wells ordinarily. Right? I've put a raft of other considerations here as lesser by graying them out and by putting them at a space on the slide where those of you in the back row probably can't even see them. But one of these, if there's a significant non-condensable gas component, as is likely in carbonate systems, then air quality or non-condensable gas disposal is going to be an issue. And so the question is, how can we take that liability and design a producing system that would turn that into a profit stream somehow? Noise. Noise is a big issue. The World Health Organization, in a 2011 report on Western Europe, concluded that every year noise pollution subtracts a day off the life of every man, woman, and child in Western Europe. To get to the point where a shale well is online, so through production flowback, now takes about, more than 1,000 large truckloads per well. So truck traffic and the associated noise and diesel particulates are a huge issue for rural communities, something to think about. And then there are the forever challenges, and Rick has already mentioned cost reduction at the top of the list. Like geothermal developments, oil and gas developments are front-end loaded, so cost reduction is a big issue, especially in the big capital expenditures for drilling, for plants, for those sorts of things. And you have to invest in those before you can realize the nickel back. Right? Then returning to the more geological theme, what can we say about flow path prediction and detection? So what kind of data can we or should we prospectively gather to build a set of case histories or benchmark data, and what must we investigate on a site-specific basis? Don't know the answer to that, but it would be nice to know. What about the subsurface do we want to know? What's going to give us insight into the extraction efficiency, the native heat extraction efficiency of the system, and the levers that we can pull to improve it? Can we link seismic attenuation and permeability? Can we pull out sub-wavelength fracture information from bulk seismic properties? And maybe Roberto will have more to say about those two things in his talk. Can we suss out anisotropy in horizontal permeability from anisotropy in geophysical measurements? How can we remotely sense the cooling front? And what are the boundaries of our convective systems? For most geothermal systems, I have no idea. And I would love to get into a lease line fight with someone about a geothermal resource, because it would be really fun. But if you don't know, you don't really know what you're talking about. So porosity and permeability preservation. What's the energy balance of the relevant mineral reactions? Are they endothermic or exothermic? And so will the temperature changes associated with production promote or hinder these reactions? Circulating fluids. These might be native or injected. Either way, or injected from a remote source. Either way, what is the refracturing time that's necessary in order to sustain these paths? Or will there be dissolution and the risk of developing some kind of short circuits that need to be remediated? In engineered geothermal systems, what is the balance of hydraulic fracturing in extension versus shear reactivation of existing fractures that's going to create the most efficient heat exchanger? Is that site-specific? Perhaps. Or are there some generalities that we can take from site to site? What heat recovery shall we expect? And Rick, you touched on this. What is the recovery factor, as we would call it in oil and gas, within our system boundaries, whatever those are? And how will evolving technology increase this over the life of the field by reducing the cost or providing new capability? And the little inset there kind of indicates that the role of technology ought to be to enable you to do things that you don't know how to do now, or to expand your comfort zone and your capacity to do the things that you know how to do now, but more efficiently or at lower cost. Yeah. So that's kind of where I'm going to wind up. So now let's go back to the beginning and look at some data. First off, that fracture porosity is always very small. I don't think this is new news to anyone in this room, at least I hope not. This table was taken from Ron Nelson's book. He wrote his PhD thesis in 1975, in which he summarized a lot of the data, and this was in there, and then later in the book, that thesis was called Fracture Permeability in Porous Reservoirs, an Experimental and Field Approach. And worth noting is that naturally occurring fracture porosity is very hard to measure accurately. And those of you who were in the room this morning and saw the rock that Joe Moore, I believe it was, passed around, will imagine if you couldn't immerse that in liquid and measure the void space in that way, how would you possibly come at an average fracture width or open aperture or whatever in order to be able to say what was the fracture porosity in that sample? We expect that induced fracture porosities are going to be lower than the natural system ones simply because of the amount of energy required to create that void space. But that's not been, well, I shouldn't say that. Perhaps Wolfgang Wawrzyk and others have done a few mine-back experiments at low scale, but we have no large-scale experiments to really substantiate that. Now, the concept matrix porosity has to provide the storage is important, as I said, because you need enough residence time for the heat exchange to occur, and the porosity, whether you're talking about the fracture system or some other large permeability pore structure that's providing flow to the wells, has to be distributed well enough that the hot rock mass is effectively contacted, whatever that means, yeah? And Rick showed some of these, and in fact, we used the same source. And And these are oil company guys. In fact, I used to work with Paul. And what these data show, as I've presented them here, is that significant matrix porosity can persist at depths of 7 kilometers, so even deeper than Rick has talked about. And I have to say, of course, that most core analysis is performed on successful wells, and our exploration dry hole rate is as high as 90%, and perhaps higher in some place. So this plot is in no way an endorsement as to how commonly such porosity might occur, but it certainly does occur or can occur in the subsurface. And in its preservation, overpressure helps, as does early hydrocarbon emplacement. The former, because porosity loss, at least initially, is largely a compaction effect, elastic or grain crushing, and then eventually ductile. And the latter, the hydrocarbon emplacement, because chemical reactions are also important and mostly tend to occlude porosity, so that anything that will slow reaction rates and protect grain surfaces from acting as nucleation sites for secondary mineralization or quartz overgrowth is beneficial. In particular, this is a time-temperature phenomenon, this chemical stuff. So time spent above about 80 degrees centigrade is the time during which quartzose sandstones are at risk for quartz overgrowth development. Cool and young is therefore better than hot and old when it comes to porosity preservation. And that's probably why the Gulf Coast tertiary sands, the blue in this graph, are more porous at a given depth than the worldwide average. It's not just an overpressure thing, it's because they're cool. But of course, cool is not what we're after in geothermal targets. Now, this is what I mean by brittle ductile transition for those of you who are perhaps not from a geomechanics background. A brittle ductile transition exists for all rocks as a function of temperature, pressure, strain rate. And at some depth, porosity will be plastically occluded if pore pressure can be released, i.e. if the rocks behave in a drained condition. And this is an example for a limestone or marble by what I mean by the brittle ductile transition. In a brittle regime, a rock has a clearly defined peak strength, as you can see from the stress-strain curve in the top of the diagram. The lower example labeled 0, 3.5, 10, so on, that's strain at the peak. Then you can see, or sorry, but the confining pressure, rather, unconfined, 3.5, 10 megapascals. You can see a clearly developed peak in the differential stress, and thereafter the rock has fractured and it has lost strength, intact strength. In the brittle, so that's what happens in the brittle regime, and those fractures are open since this is a uniaxial load in the orientation parallel to the maximum loading direction. It would be opening perpendicular to the minimum principal stress direction if there were true triaxial differential stresses. And they may also fail in shear at higher confining stresses, and then you get conjugate planes at 30 degrees approximately, or whatever the shear angle is, and that's a rock property to the maximum stress orientation. However, as the confining pressure is increased for these room temperature samples, these are all at room temperature, so I'm only looking at the effect of confining pressure here, the nature of the deformation changes. You no longer see a clear peak strength in the rock. You may see a strength and then a slow decline, or you may continue to see essentially hardening as you continue the ductile deformation. And the rock yields at and bulges out without macroscopic fractures actually developing, and that's shown by comparing the samples on the left, which are from the brittle regime, with the barrel-shaped samples on the right, where you'd be hard-pressed to find an individual failure plane, even if you took a thin section of those samples. Yeah. And Not all rocks are created equal. The brittle ductile transition depends on lithology, and you can go through an exercise of mapping out the brittle ductile transition for prospective Sedheat horizons as a function of whatever geothermal gradient you think you have and as a function of whatever lithologies you think you have. And this is an example I put together actually about 40 years ago now from data in the Handbook of Physical Constants. That was GSA Memoir 97. Thank you again, GSA. That was an invaluable document. Many of us remember it fondly, I'm sure. And from various other references that were lying around Bill Brace's lab. And it clearly demonstrates that limestone, which is shown in the circles, filled and open, is a different mechanical animal than dolomite, which is shown in the squares. The nature, what's plotted is the nature of the failure at a given temperature and confining pressure. Was it brittle or was it ductile or was it sort of transitional? And so you can see that the different fields illustrated on this graph. And this inequality is reflected in the fact that, for example, all the deep Ellenberger production in West Texas and in New Mexico is from dolomites. The limestones are tight, as you would expect, at depths below perhaps even 15,000 feet in a normally pressured section, let alone 20,000 feet or more. Yeah. And we're often very sloppy about our usage. We say carbonate, but we don't inquire exactly what is it. And limestone and dolomite happen to be mechanically very different beasts. Can also be true in siliciclastics. Pure quartz arenite is going to behave in much different fashion than something that's got a high component of ductile or even feldspathic grains. They're just going to be mechanically different. Yep. Chemical reactions also play a significant role, and as I said, I believe most reduce porosity by cementation or by pressure solution, and I think that's the general view in the oil patch. And all this is going to be fodder for session 6, so I'm just going to mention a few highlights here, and if anybody who's got something to say in session 6 wants to get up and protest at this moment, I will give you space to do so. So to find porosity preserved at depth, you need to look for play fairways in which cementation and dissolution at grain contacts has been inhibited. We know that things like chloride coats inhibit cement. Early hydrocarbon charge, I believe, inhibits cement. That's controversial in some places, but my experience has been in that way. There are indeed some reactions that create or enhance porosity, and Rick is correct in that many of these are in carbonates. Karsts also, if you have mole replacement of limestone by dolomite, that is a volume, a decrease in the volume of the chemical material. That's about 14%. So that can create quite a bit of porosity, and I believe that's actually, myself, I believe, that that's responsible for a lot of the porosity that you find in the Scipio-Albion trend. So we do know that there are places where that happens. And there may be other kinds of reactions that are important locally in creating porosity, but those would be for reasons that are difficult to predict pre-drilled, so they're going to be very difficult exploration targets. You may find that the only porosity that you have is actually chemically created, but I would argue then that you probably don't have very much porosity in those rocks at all. Not enough to provide you the storage that you're going to need if you want to have a viable geothermal prospect. Now, fracture porosity may or may not decrease with depth in the same way as matrix porosity. Mechanical and chemical processes affect both fractures and matrix porosity, but different chemical fluid systems and pore pressure regimes may occur in both due to the open and closed nature of the two distinct types of void space. And I think maybe we'll see some of that, I hope so anyway, in the session on basin evolution and fluid flow characterization, and in session 6 on diagenesis. Now, while dissolution may create matrix porosity in the subsurface and overpressure may preserve it, tectonic processes are generally accorded to create fractures in the brittle regime with the potential maybe not to induce significant porosity, but certainly to give you quite a bit of transmissibility, and that can occur at all depths depth ranges in that regime. And certainly we do have sedimentary rocks and igneous and metamorphic rocks that are well in the brittle regime to any depth that we might find it convenient to drill or economic to drill for geothermal resources. Yeah. Now, the fracture intensity induced by tectonic forces depends upon the things here. Rock strength and brittleness I've listed in gray because it's not a tectonic process. It's a rock property, but I believe it's important, if not governing, in the resultant fracture intensity, because I actually don't think that any rock is strong enough to resist deformation in the earth unless it's surrounded by ductile materials that are actually taking up the deformation on its behalf. We can argue about that if you believe differently. Curvature. That's illustrated for the two rock types on the right in a plot. In a plot of the number of fractures per foot, which is a measure of fracture intensity, versus the present-day radius of curvature in the sedimentary horizon at the measured location for these data. Now, I should, of course, say that it depends on curvature through time. And if I folded and unfolded layers, then what I have in the way of fracture intensity may reflect inherited structure rather than the present-day structure. So I need to take this with a grain of salt. But again, present-day stresses being important in governing what are opening fractures, it may be that you will nonetheless get guidance as to the orientation of the open fracture permeability, the transmissibility, the preferred directions, from looking at present-day curvature. Yeah? Strain rate. We know from lab experiments that both brittleness and apparent strength increase with increasing strain rate. Thus, so should fracture intensity, but I don't know of any field studies that assessed strain rate differences and compared them with resultant natural fracture intensities, and I'm not sure how you would unpick strain rate difference from radius of curvature differences. Yeah. So maybe some of you in the audience have data to address this, but I am not aware of any of that. And then there's some secondary variables. Again, I've grayed out bed thickness because it's a depositional given, not an aspect of tectonics themselves, but it may be a secondary influence on controlling fracture spacing.
One question?
Yeah.
The second derivative is the rate of change in
Dip.
fractures with pressure?
The second derivative is the rate of change of structural dip. It's a curvature measure. That's all. Down at the bottom of the slide is the number of fractures per foot, which is a measure of structural intensity. On the y-axis is the curvature, which is it's the second derivative of the surface. Okay, it's just
Which surface?
the structural top of the bed boundary for which the fracture intensity is given, present day. Okay. So the caveat was, I really need to look at all this stuff through and its evolution through time in order to understand the inherited grain and everything that's really going on. All right? Yeah. Yeah. Okay. And then there are other things that go on too. If I'm looking at different rocks mechanically, they may deform differently. So in this case, I've got gouge-filled fractures in my 10-sleep sand, whereas the Madison Formation, Rick, back to your point again here, I have open fractures that would be more conducive to having fluid flow through them. So there are always buts and ands that go along with studies of fracture intensity and fracture permeability. Okay, Caesar said it, and I guess I believe it. Fractured reservoirs can be considered as trifold, yeah? And the way I put this is fractures provide both storage and the conduit to the well. And in this case, we're toasted for geothermal, as we won't get the storage volumes that we need to enable heat transfer. So we can forget about that first type. right? Which may be one of the problems with EGS, but I won't go there right now. In the second instance, fractures enable economic production rates by augmenting matrix flow rates, and this is sometimes referred to as a dual porosity system, but the nomenclature is kind of deceptive. It's more about flow characteristics. And in the third instance, fractures might be present, but we don't really care because they're insignificant to system performance in that matrix porosity and permeability are sufficiently large to mask any contribution that they might make. And this is not an uncommon situation in the oil patch, though we may still find it useful to frac pack wells in the near wellbore regime, but that's for slightly different reasons. But I don't know when it comes to geothermal wells. And as I said, this framework is a somewhat arbitrary partitioning imposed upon a continuum set of behaviors, but it's sometimes helpful for focusing your thinking. And the same can be said to hold for hydraulically fractured reservoirs or wells. In this case, I may have two different permeabilities associated with the natural and the artificially induced fracture sets. I would argue that I'm probably not actually going to be able to see that different permeability associated with an introduced fracture set because it's going to get lost in the wellbore storage. But where's Derek? Because he may have an opinion on that, and so I will defer to him.
Okay, directional permeability would be part of the same discussion then?
Yes. Yeah. And we can come back to that because it's part of the whole anisotropy thing. I think you're far more likely to get significant permeability or transmissibility anisotropy in fracture networks, even in natural DFNs, if you like, rather than artificially induced ones or idealized ones, than you will in matrix permeability due to sedimentary, depositional, and diagenetic effects, but never say never. So is geothermal for electric power generation, even in sedimentary basins, restricted to reservoirs in which there are fractures that augment matrix flow rates? I don't know the answer to that question. I do know that 30 to 50,000 barrels of fluid production is a big ask. Okay? These are some oil field examples. Oil field majors BP's most prolific wells barely get into that range. 5 of our 15 most prolific wells were located in Azerbaijan in 2009, and that's probably still the same today. And of those, 5 were at a field called Azeri Sherag Ganashli. And the 5 platforms in that ACG field are shown here, and the average rate of the oil wells is shown in barrels per day, and I have enhanced that rate by 1.5 times to give you an average rate in the final column to account for water production and maybe some associated gas production. There's not very much water production in these fields at this time, so I didn't add as big a factor as you might for other areas which are producing more. But you can see, even corrected for or augmented for any water production that might happen, we barely get into that range that you're looking for. And it's not just BP shown here. As Rick alluded to, in 2012, Chesapeake Energy said it drilled the largest oil gusher in the company's 23-year history at a significant discovery in the Anadarko Basin. And this is with 2012 drilling technology and completion technology, okay? And the Thurman Horn well in the Hog Shooter Formation produced 5,400 barrels of crude a day during its first 8 days of production. Okay? 5,400 barrels. And its first 8 days of production probably wasn't making a lot of water. They probably cleaned it up before they started talking production rates for the analysts. Okay? 1977 discoveries in the Williston Basin initially produced up to 6,000 barrels a day from Mississippi and Lodgepole carbonate mounds. Yeah? And these were the best wells drilled in the onshore lower 48 in decades. You're talking 6,000 barrels a day. But we all know that actually where it's at is in the Gulf of Mexico in the lower 48. It's not actually onshore, but it's just offshore. And the highest single flow rate for a single well flow rate in the Gulf of Mexico as of 2010 was just over 46,000 barrels of oil per day based on the average daily rate in the peak month of production. Peak month of production. Okay? Again, I could increase these by a factor of 2 or 2.5 if you like, but I'm talking about the top 50 wells in thousands of wells, even if you think they're all capable of producing at rates that are attractive for geothermal. And we don't stint when we're trying to drill and complete deep water wells in terms of the type of completions and the size of hole that we drill. We drill these things to be big wells, and if they're not, it's because the reservoir really isn't capable of delivery, not because we've got some kind of restriction in the well bore, at least during its peak production times, that would prevent us from producing more. Yeah? Now, there are some monster wells. The Cerro Azul, in Poza Rica, I think that was, came in at 260,000 barrels a day. You know? Shot crude oil over a 2-mile radius. Okay? At that time, that was considered to be a success. But over the next 14 years, the well produced 57 million barrels, which is an average daily rate of 11,200 barrels. So asking for these high rates for 30 years is asking for a lot. So that brings me to the next question then. How can you tell what kind of a system you're dealing with? Does it have fractures or not? Well, I'm sort of simplistic, so I kind of go back to, is there any evidence for fracturing at all? And I rely on my 5 senses. And since most of us are visual learners, myself included, I rely on what I can see pretty heavily. So core, if I have any, and the trick here is to separate drilling-induced fractures from those that were there before. Borehole images, electrical, acoustic, or whatever, these are really good, and they create an image of the borehole wall, and it looks sinusoidal when you unroll it because of the way the fracture intersects a more or less cylindrical wellbore wall. You can look for more subtle things like cycle skips on sonic logs, or if you have radioactive mineralization in the fractures, you can look for spikes in the gamma ray. Mud logs, smell. Were there changes in the chemistry of the return fluids in selected intervals that might indicate differing fluid compartments interchanging over a single depth interval? Now, this doesn't work very well for fine-scale fracturing as the signal gets too diffuse in the return mud stream, and it certainly works best if you're drilling close to balance. But I have used it before to identify fault intersections and larger scale fractures. Touch. How do you touch, you say, remotely? Well, again, through the drilling records. Were there evidence of bit drops indicative of large apertures or large moldic porosity? Was there evidence of fracturing from drill string seizure, perhaps caused by caving or spallation? These sorts of things can give you indications that you might be dealing with something other than just routine matrix porosity. If you're on a drill floor, sometimes you can hear these kinds of events, so you can use your ears as well to inform you. Yeah? Taste. I don't know how to do that, but never say never. Maybe somebody's got some kind of taste discriminator for fractures. I would caution that you can't see what you don't recover. And you saw some pictures of core this morning, and some of it was pretty rubbleized. And I would say many times fractured intervals jam or grind up in the core barrel and never make it to the surface. However, image logs are not infallible, and because of the oblique borehole intersection or erosion by the drilling process, the apparent fracture apertures may appear larger than actual. Or you may see fractures evidently more frequently than natural. And so the experience in this illustration, where you can see in the yellow the borehole image log identified fractures, and in brown the ones that were found, larger ones that were visually found in the core, that's not atypical. So having information from a multiplicity of sources is always good. And I don't want to say the FMI log fractures weren't there, because they probably were. What I don't know, and what none of these tools will tell you, is what about the transmissibility of those fractures? Right? Now, there are things that will enable you to consider flow contribution from various horizons in the well bore, but of course the well has to be flowing for those tools to work. And so we have things like spinner surveys, and I've given Schlumberger a free piece of advertisement here with their flow scanner tool. But this is a really nice thing, because if you have 2 phases or multiple or even 3 phases flowing in the wellbore, this is the tool for you, because it has both electrical and optical sensors, and so you can distinguish gas from liquid and you can distinguish oil from water, assuming the brine has some kind of conductivity associated with it, and the oil does not in general, by looking at the resistivity measurements. So that sort of stuff works very, very well to identify where the flow is coming from in a well. Distributed temperature surveys have been used, and that uses Raman scattering. It's just a cable, so I don't really have anything to illustrate here, but there's a lot of processing that goes on to separate the Raman signature from the Rayleigh and Bruin scattering. Yep. And I'd say that there are newer generation optical fibers that work pretty well up to 200 degrees centigrade. They're trying to mitigate, if not completely remove, the hydrogen darkening that has plagued things, but they still fail way too often. So more there would be good. Tracer tests are not routinely used in the oil and gas industry. Even using them to interpret residual oil saturation is above the expected competency of most of our staff. So where's Pete Rose? Are you around here? There you are. Okay, good. So if you have anything you want to know about tracers, I would certainly refer you to him. We do use reactive tracers to assess residual oil saturation, and we do use non-reactive or conservative ones to investigate interwell transit times between injectors and producers, but this is not commonly done. And Pete does much more complicated things than that, so I look forward to hearing what he has to say. Pressure transient analysis, where's Derek? Yeah, there. This is sometimes called well test analysis, and we try to interpret system pressure temperature, or pressure time, or rate pressure time response in terms of models. You assume a 10% conversion efficiency. Yeah.
Is it fair to assume that the more, as you put more fractures in, more uniformly distributed and uniformly sized fractures, you're approaching a porous media, and so porous media has the optimal, a porous media instead of a fractured media has the optimal performance or potential?
What a segue. What a segue into the next slide. Yes, I think it is, right? Because I think the more homogeneous, the more isotropic a porosity permeability system I can have and still be economic, get economic throughput through there, the better off I'm going to be when it comes to efficient heat extraction from whatever volume I'm trying to contact. Right? And the problem is, of course, that permeability anisotropy is so common. In sedimentary rocks, first they're deposited in layers, but even at the finer scale than that, they were still deposited by water or wind, and that has a flow direction, so I have horizontal anisotropy as well as vertical anisotropy at the fine scale. And then at a somewhat larger scale, I've got the sedimentary facies, so I have channels, and then I have overbank deposits, and then I have structuring on top of that, and then I have fracturing and all of that. And all of that is going to create a more heterogeneous, more anisotropic case. And it's not a question, in this case, of I can aggregate all that up into a great unwashed representative volume. And the reason that I can't is that permeability is controlled by the connectivity of the extreme values. It's not like porosity, where it's a volumetric average. So it matters whether there's a tight zone through the whole thing, no matter how thin that is. And it matters whether there's a high permeability pathway, no matter how tortuous that really is. Okay? So that's really the issue here. Yeah? Okay. So I think that's all I will say at this point, and I will leave it to you to decide on the similarities between what you heard from Rick and myself, and we will open the floor for any questions for either of us or any discussion from the audience about points you'd like to raise in response to this. Yeah. Yeah.
Yeah, I think you've done an excellent job of proving that natural fracture systems are not going to work for us. So what about producing our own fracture systems? And I don't mean and hydraulic fracking doesn't work either, because as soon as you hit SH min, you just start opening up the pre-existing fabric directions that control also the natural fractures. And everything gets drained off into them, and you don't...
Well, actually, that happens below SH min, but now we quibbled. Yeah, okay. Yeah, right, yeah.
So the point is that that's
So what do you have in mind about engineering a fracture system?
well, producing rubbleization.
Gas buggy 3.
Rubbleization, it requires propellant. And I think a few places it's been done, but what it does is it produces a network, a fine network of fractures. And what one can then do to sort of activate that fracture system is you then do, these below SH min, you increase fluid pressure below SH min, and that'll cause, the fractures that are properly oriented for shear, that are going to be conductive, to activate, and then you'll start a flow system.
Yeah. Well, this is my personal opinion. Okay, so first off, the energy required to rubbleize significant volumes of rocks, essentially do something more than give you a bigger effective wellbore radius into which to produce, are so large that it's likely to be an economic non-starter. Secondly, and that's the main issue there, but in rock anyway, because it's got a multi-million year, or sometimes multi-hundred-million year history, it's got fractures of all kinds of different orientations. So you already have the possibility to inject, if you're patient enough, below the minimum stress, and potentially reactivate favorably oriented shear zones. And we've tried this. So far, if that's all you're doing, not with a whole lot of success. My own view is that the right approach to take is sort of exactly the one that's being taken, which is to extend what is now not economic as a hydrothermal system by created fracture networks, however you want to engineer those, or by drilling forks and fish bones or something else that would contact more rock in a favorable orientation, and make those marginally economic things economic. Learn as you go how to do those things more efficiently, and then you'll be able to tackle the more difficult rocks, the tighter rocks, the tougher targets with your improved technology. But that's a long-term proposition. Roberto and then Joe.
You talk about two things that caught my attention. One is the need of porosity, the need of resident time, because you need to take as much heat as possible with a high thermal capacity fluid. What about converting that thought of high porosity into high surface area instead?
Happy with that.
And the fracture surface area is very limited compared to the matrix fracture area. And then using the terminology that we use in the whole industry to come up with the concept of the effective surface area, because the moment that you have a fifth zone, you are talking about this, you fracture, it doesn't matter what your surface area of the matrix is, you're going to lose that possibility. So if we start using these concepts of your effective surface area, your surface area, and the resident time, we might then start realizing why some of these concepts are just not possible, because either you don't have enough surface area or either you don't have enough resident time.
Certainly worth looking into. Yeah, Joe?
We're talking about barrels, because they're very basic questions, so bear with me. So 30,000 barrels a day, that's 875 gallons per minute, which is sort of an okay one.
Yeah.
In geothermal.
Yeah.
And when I look at these, 1,000 gallon per minute wells, we're looking at 8.5-inch wells. Are we looking comparable dimensions and flow rates? Are we looking at, tubes?
Yeah, so some of the wells in the offshore now are completed with 9 7/8. So they're even bigger. Many of them are 7-inch, which is smaller, but I suspect that the producing length is larger than what you are dealing with in your geothermal systems because they're drilled.
Very, very similar wellbore diameters, and so our flow rates are going to be reasonably comparable. And I really found your talk eye-opening. If this is the kind of upper end flow rates we might expect.
Roberto, Schlimmers, you got any ideas for getting something much bigger out? I mean, what we do is we add another lateral, basically.
Sure, but,
Yeah.
800,000 gallons per minute is not a huge geothermal well.
No, it's not. It's not. Derek, and then I'll come back to you, Sid.
Yeah, those numbers I think are quite encouraging. I did the calculation. I think half a kilobarrel a day is about 100 kilograms a second. And so that's the number that's sort of banded around for EGS wells, and some wells. So I don't know what the distribution is of wells in that range. And of course, it depends on the temperature you're tapping as to what amount of energy you get out of it. But those are perhaps in the right ballpark. The other part is, as well, is if those are made in unfractured reservoirs, porous reservoirs, then the issues of short circuiting, not only in terms of intrinsic short circuiting that Rick was showing in his calculations, but the feedback short circuiting of opening fractures by thermal contraction is much lessened, and so maybe you can get better.
Well, and I think the other thing that probably happens is because they do have high matrix permeability, that you would get spallation or grain boundary breakage within the matrix, and you would sort of disaggregate that. That might be actually augmented by the fact that quartz has very different thermal expansion along the C-axis versus other directions. So, yeah, Sid.
If one thinks of either injecting from a wellbore or producing into the wellbore, then one has the convergent flow or divergent flow into this wellbore, and one may well need some way of enhancing this permeability or the fluid flow ease around the wellbore. And indeed, something like rubblization really comes in as a real possibility now to effectively give you a much larger wellbore in order to allow that convergent or divergent flow to or from the wellbore. That's probably going to be essential in these wells of very high flow rates, 50,000 barrels a day or so.
Sid, you raise a very good point there. There may well be a role for that. And certainly what it would be competing with would be frac backing. But, then you get into, do I know of any proppants that are useful for high temperature systems? And I can imagine no better proppant than the rock itself, which is what you get from rubblization. Yeah, Rick.
If you're thinking carbonates, acidization obviously is an old technique, but it's highly relevant on the injection side anyway, for opening things up. Just
Good point.
The pH, even not severe, just dropping the pH a bit. So you're wanting to do it out in the reservoir. Maybe enough on the timescales we're talking about, and being economic, acetic acid or something in the oil industry is just dropping it a few notches. And hoping over the decadal time scale, we're actually doing some
Good. Yeah. Wait a minute.
I have a question to Rick.
Yeah.
You came up with this magic number of 30 years. Right. Of course, the decline curves may speak for them. But can then you put on the label of renewable energy on this?
The question was,
If you're just looking at a 30-year life cycle, is it renewable? I would say, if we could make this work, think of the scale of the basin, not the modular unit I just showed here. The sort of visual thing that I was thinking of, you can make it work on a 25 megawatt unit or 100 megawatt unit at 30 square kilometers, and we've got basins that are 100 kilometers in scale. You just work your way up the basin in terms of mining heat, laterally, whatever. So even though you might mine out the easy heat locally, you've got a large resource we keep coming back there, and it's stratigraphic. Hopefully you've got a good horizontal dimension you can move through in a low population area.
Add this to your text that will have the politicians.
okay. Sid?
If you think of like needing 30, 50, 60,000 barrels a day, and you look at this 100 millidarcy formations, that's quite doable from a borehole with a little bit of stimulation around it, whether it's frac pack or acidizing or rubbleizing. I think the issue is whether you can really sustain that more than a few days.
Yes, sir.
And you know, we haven't talked about scaling or solids dropping out as you change pressure and temperature, and so the numbers work. So if you look at a borehole, yeah, you can get 50 or 60,000 barrels a day from a reasonable length borehole. The question is, can you sustain it? And you know, I would say, never mind this 30-year stuff. No banker is going to believe that anyway. You got to look at what will it do over 2 or 3 years, 5 years tops. And there's certainly nothing wrong with reworking the well as long as the economics are there. A banker would much rather see you rework the well over 2 years than try to sell them on a 30-year life.
That's absolutely right. That 30-year life presumes no intervention in the moment, I think, and we all know that that doesn't happen even in the oil field. You have to go in, something fails mechanically, you've got to replace pumps, or you've got to do something to work the well over. That's a significant capital cost.
But
Joe?
we produce geothermal systems from carbonated rocks for tens of years. Scaling is not necessarily an issue in conventional geothermal environments.
Yeah. But it is true, we learned this morning that the salinities that they're talking about in these geothermal systems are very fresh. Yeah.
Until now, I didn't hear anything about cost. What is it they're paying? In Europe, the limestone is not so geothermal fluid production for karstic formations. How about the US?
I will turn that over to Rick and to Joe, but certainly karstic horizons are very attractive in terms of Sedheat targets. But Rick, do you want to say anything, or Joe, do you want to say anything about production from karst? Or, yes, Dave. Yes, David.
I'll put it the other way around. Most of the injection disposal in the Barnett Shale is into the karst-Dellenberger limestone, which is immediately below the shale. In fact, that's one of the really big advantages of the whole system. And one well can take tens of thousands of barrels a day, unless you put it in your fault. Then it might be incredible.
Yeah, and as long as it's dolomite, that porosity should still be preserved at great depth. Yes.
But again, I have in mind what you said is resting time. If you have fractures, you lower your resting time, now your temperatures will be considerably lower. And you know, Sid says he's going to work on a 200 millidarcy reservoir. I will argue, provided that it doesn't have fractures, because if it has a couple of fractures, it's not going to work.
That's right.
And so that seems to be the problem, that we want a homogeneous, uniform, massive 200 millidarcy reservoir, and that's not going to happen.
Well, I don't know.
You said it flow.